All right, if you're in precalculus, you have definitely run into logarithms. And let's be real, they can look a little scary, right? But what if I told you they're built on something you already know, something you use all the time? Well, let's dive in and unlock what a logarithm really is. So first things first, why do we even need these things? What's the point? Well, think of logarithms as a super specialized tool. They're designed for one job and one job only, to help us find an unknown exponent. Yeah, that's it. A logarithm is just a fancy way of asking the question, hey, what power do I need to stick on this number to get that result? And that question, well, it leads us straight to the one core idea that's going to make all of this click. Okay, here it is. This is the big secret, the single most important thing you need to remember about logarithms. If you can burn this into your brain, I promise, everything else is going to fall right into place. A logarithm is an exponent. That's it. It's just wearing a disguise. So keeping that key idea in mind, that a log is just a hidden exponent, let's check out the official definition. We'll see how we can basically translate back and forth between exponent speak and log speak. Now, look closely at these two equations. They aren't just related, they are literally saying the exact same thing. Over on the right, you've got the good old exponential form you know and love, b to the power of y equals x. But on the left, you've got the log form. All it does is rephrase that statement as a question. The power y I need to put on b to get x is, see? They're just two sides of the very same coin. Okay, let's make this crystal clear with a real example. We all know that 2 to the 5th power is 32, right? Simple. Now, look how we write that in log form. Log base 2 of 32 equals 5. Notice how all the pieces are still there? They're just shuffled around a bit. The base is 2 in both cases, the final result is 32, and what does the logarithm equal? It equals 5, the exponent. See? That's its entire job, to find and isolate that exponent. All right, enough theory, you get the idea. The best way to really get this stuff is to roll up our sleeves and actually use it. So let's jump into a few examples and see how this little translation trick helps us solve some actual problems. Okay, let's start with a nice easy one, just a simple translation. We're given log base 5 of 125 equals 3. So, step 1, let's identify our players. The base, our b, is 5. The answer to the log, which remember is always the exponent, is 3. And the other number, our result, x, is 125. All we have to do now is plug those pieces into our exponential form, b to the y equals x. And boom, we get our answer. 5 to the 3rd power equals 125. Simple as that. All right, ready to level up a bit? Let's try a slightly trickier one. Log base 4 of 164. So what's the question we're asking? We're asking 4 to what power gives us 1 over 64? Well, we know that 4 cubed is 64. But how do we get that fraction 1 over 64? This is where you got to dig back and remember your exponent rules. Remember what a negative exponent does? It flips it. It gives you the reciprocal. So to get 1 over 64, the power has to be -3. Okay, check this one out. Now we're solving for a totally different piece of the puzzle, the base itself. We've got log base b of 81 equals 4. The first step? It's always the same, no matter what. Just rewrite it in exponential form. That gives us b to the 4th power equals 81. And now it's not a log problem anymore, is it? It's just a little puzzle. What number times itself 4 times gives you 81? Well, let's see. 3 times 3 is 9, times 3 is 27, times 3 is 81. There it is. The base, b, has to be 3. Okay, listen up, because this next part is super important. There is one specific mistake, one trap, that almost everybody falls into when they're first learning logs. Let's make sure that's not you. Here's the pitfall. People confuse log base 2 of 8 with 2 to the power of 8. You have to understand, these are asking completely different, almost opposite questions. 2 to the 8th is about making a number huge. It's asking you to grow it. Multiply 2 by itself 8 times, and you get this big number, 256. A logarithm, it's like a shrinking function. It does the opposite. It asks for the small, tiny little power you need to get to 8. And in this case, the answer is just 3. Totally different worlds. So at this point, you might be thinking, okay, I get it. It's a math thing. But where on earth am I ever going to see this in the real world? Well, it turns out, logarithms are absolutely essential for measuring some of the most powerful and frankly terrifying forces in nature. And the perfect example of this is the Richter scale. You've all heard of it. It measures earthquake strength. Now, why do they use a logarithmic scale? Because without it, the numbers would be absolutely bonkers. You'd be dealing with numbers so huge and spread out that the scale would be completely useless. So here's what that actually means in practice. When you hear about a magnitude 7.0 earthquake, it isn't just 1 point stronger than a 6.0. It's not just a little bit worse. Because the scale is logarithmic, every single whole number you go up means the ground is shaking with an amplitude that is 10 times greater. Now let's take that even further. How does a magnitude 8.0 quake compare to a 6.0? It's not just 2 steps up, it's 10 times 10 again. That's 100 times stronger. We're talking about a massive, unbelievable difference and destructive power. And it's the logarithmic scale that makes it possible for our brains to even comprehend that. So, I'm going to leave you with a little challenge to test your understanding. Based on everything we just talked about, how much stronger is a magnitude 8.0 earthquake than a 5.0? Really think it through. When you figure it out, you'll see just how powerful this exponent in disguise truly is.